members and returning members and members from across the RASC. I see we have a few of them online, so it's always nice to see you here. I'm going to do a small introduction of our executive so that people know who our executive is. Susan Gagnon, treasurer, just wave. Acer Elgindi, is he on yet? No. Lori Graham, who is going to be speaking with us this evening. Editor Kevin Kell. Librarian Francesco Ambrogi. And National Council Rep John Hurley. Honorary President David Levy. And myself, President Kim Hay. So I will carry on with our announcements. The RASC-KC is celebrating its 60th anniversary this year. And of course, if we were able to get together, we would have we would be able to have dinners and observing sessions and everything else. But since we cannot, we're going to be doing everything through online here or in our newsletter. So maybe by the fall we can get together. And that's what we're hoping for. The RASC Weekly, you should have received that in your email this week, called Planets Insider's Guide, Moon at Noon, and the Golden Age of Islam. So check your email for that. It's quite a few interesting topics in there. Fallen stars might be possible in September. We're still in discussion with Belleville Center, and hopefully all of our health restrictions will be eased up by then as we get our vaccines. The RASC General Assembly is being held June 25th to the 27th. And I have it from Roland Deshane that on the 28th, there's going to be a virtual field trip to the ALMA and U of Alberta Meteorite Lab and the Roberta Bondar Observatory run by the Baca and Wood Buffalo Astronomical Society of Fort Smith, Ontario, or Fort Smith, Northwest Territories. So that will be that'll be very interesting. The schedule is being fine-tuned and we will know about it. So just keep track on the General Assembly webpage. And I have it from okay. Thursday, this is tomorrow, April 15th, 12 to 12:30, Moon at Noon. If you want to get out there and do the Explore the Moon certificate, now is the time to do it. Tonight is actually the first night of minus Q5 that we're supposed to be observing. And in our local area, we're going to have about an hour of clear sky, well, 44% cloud and then 85% cloud, 10 o'clock onward. And the sun sets at 10:34, or moon sets at 10:34. And so they say that things could get a little messy. And if you want to join in, bring the materials you would normally use for chocolate chip cookies. So that sounds very interesting. So in order to get ourselves underway, David Levy is going to do the introduction for the night and read us some poetry. David. Oh, unmute, dear.
Me? Good. You can all hear me, I say. Okay. I'd like to add my welcome to you, and I hope that you have at least 42% clear at your next event, because I cannot observe if it's 43% or more, but if it's less than that, I think I can observe, and I think we'll be able to. Or did I get that backwards? Well, okay. I want to add my welcome to your presidents. I think this is wonderful. It's wonderful to be here, and it is such an honor that with the one of the real advantages of doing it this way is that I can come to all your meetings and your social events. And it is such a pleasure for me to do that. I'm going to do my little poetic quote to get our meeting started tonight. It's by Robert Record. It's from the Castle of Knowledge, and he published it in around 1556. This is about 10 years before Shakespeare was born. And he wrote, "If reason's reach transcend the sky, why should it then to earth be bound? The wit is wronged and led awry, if mind be married to the ground." Thank you. Let's enjoy the meeting, and back to you, Kim.
Thank you, David. Okay, we are going to carry on with our first speaker, who is our Vice President, Lori Graham. And she's going to give us a talk on a tale of two toric terrestrial bodies. Now, try saying that 3 or 4 times. However, this week, this week, Lori was actually in the news, and congratulations. I don't know if you got all the congratulations off the list, but way to go. So I'm going to turn the floor over to you, Lori.
Thank you. Let me just set up my screen share here. Okay. Good. How's that looking?
It is looking awesome.
Okay, let me just bring up that. Good. Okay. So I haven't given this as a presentation before. I don't know really how long it's going to take. I'll try to keep within the sort of normal time limit. The reason that I made this presentation was that I decided to, expand my horizons a little bit. And I took a course called Introduction to Geology over at St. Lawrence College. It was actually an online course. And then we got hit by COVID. And I decided, well, if you take 7 classes, you can get a certificate in geological sciences. So then I followed up with mineralogy, and I'm currently just finishing up oceanography. So I thought, well, maybe I could do something for this geology class that will sort of overlap with the RASC so that I can kill 2 birds with 1 stone. And I decided to talk about planetary geology. And I had a really hard time picking my favorite moon. And so I decided, well, since I can't pick 1 moon, I decided to pick 2 and to compare them. So I'm talking tonight about Io over here on the left and Enceladus on the right. And let's see if I can get how do I march through the slides? Okay. Oh, always something. Why are these buttons not working?
Page up, page down, left arrow, right arrow, enter.
Yeah. Okay,
There you
enter.
go.
All the other buttons aren't working. So most of these images came from NASA or from JPL. And these I'm free to use for presentations like this, as long as I cite where they came from. Unfortunately, most of these citations are in the notes section, which you're not going to see. So I put a bunch of them at the end as well. But I just want to make sure that, I'm not plagiarizing anyone here. And you guys all know what planetary geology is, so I'll skip over that. And I'll just sort of review the solar system. So we've got 4 terrestrial planets that we can study for geology, and that's Mercury, Venus, Earth, and Mars. And for the most part, Mercury is geologically inactive because its core is no longer hot enough to sustain volcanism. The Venus is hard to observe because of that dense atmosphere, and it's, of course, really hot, about 460 degrees Celsius. And the problem with it is the atmosphere can't really see through it. So there's been a lot of imaging done, and it does appear that there are actually active volcanoes on Venus. And of course, we have them on Earth. And then poor little Mars, being only about half the diameter of Earth, it has cooled down. And although it had a lot of volcanism in the past, there's nothing active on it right now. So there's still, of course, some geological events such as erosion happening, but for the most part, it's not doing that much. Now the other, of course, the gas giants, it's kind of hard to do geology on them, but fortunately they have a lot of moons. And it's interesting that Europa, which is the second Galilean moon out from Jupiter, actually shows some evidence of plate tectonics similar to the Earth. So there's places where it looks like the icy crust is separating, which would be equivalent to how the the ocean plates are separating in the middle of the Atlantic Ocean. But Io has always been my favorite moon, and it's I just love it because it's so geologically active, and it's the only body besides Earth and Venus that's known to have active volcanoes. Now, Saturn also has a ton of moons, and 7 of these are large enough to, collapse under their own gravity to form a spherical body. And of course, Titan is, pretty amazing, and it's the 2nd largest moon in the solar system. And it has what we call cryovolcanoes that are different from the volcanoes of Venus, Earth, and Io, because in the case of Titan, these are mostly water ice that's spewing out of these. And Enceladus, which is quite small, it's only the 6th largest moon of Saturn, it also has cryogenic activity. So looking at Io, it's named in a similar fashion to most of the other moons of Jupiter. Io was a lover of Zeus. So Zeus was, he had quite a few children, and some of the moons are named after his children as well. And it's about 5 times further from the sun than the Earth is. So it only gets a little under 4% of the light energy that we do. So the heat that's driving this, things on Io are certainly not coming from the sun. And it's quite a bit large, it's a big moon relative to most of them in the solar system. It's almost 30% the diameter of Earth. And it being the closest moon, it actually orbits Jupiter very rapidly, once every 1.8 days. And this is really important for why it is like it is. So it was first discovered in 1610 by Galileo. And from Earth, image A is pretty much what we see through, a backyard telescope. And the first time that we really saw it was in 1974 when Pioneer 11 flew by, because Pioneer 10, its camera was obliterated before the flyby. And this is what we saw, but it really wasn't until the Voyager spacecraft that we got a good look at this moon. And you can see here that it's absolutely fascinating looking. And this was later enhanced by the images that were captured by the Galileo spacecraft that was at Jupiter from 1995 to 2002. And then we had images from Cassini as it flew by on its way to Saturn, and New Horizons on its way to Pluto. And so we do also have Juno is currently at the planet, but it's really not focusing on the moons. It's focused on Jupiter itself. So here's a lovely close-up that was taken by the Galileo spacecraft of one of the craters. So the second subject is Saturn's moon Enceladus, and Saturn's moons tend to be named after giants and titans from Greek mythology. And it's almost 10 times further from the sun than Earth, so it only gets about 1% of the solar radiation. And the other thing about it is it's quite small. It's only 500 kilometers in diameter, and it's Io is about 7 times larger in diameter. But similar to Io, it orbits Saturn rapidly, once every 1.4 days. So Enceladus was discovered by William Herschel using a 1.2 meter reflector. And the first close glimpses were offered by Voyager 1 and 2 during their flybys in the 80s. And we really started to get a lot of great information with the Cassini orbiter that imaged Enceladus during its mission that started in 2004. So now the thing I hate about these Zoom things is there's no feedback. So I can't read the audience to know if my pacing is okay.
Yeah.
Thank you. If you need me to slow down or if there's questions or something, just interrupt me. So even though they're very different, they do have something very important in common, and that is that they're both spewing material out into space. Now, when you look at them, Enceladus is very white and very bright, and it's actually one of the brightest objects, or the most reflective objects in the solar system, with an albedo of 0.81. And that means that it reflects 81% of all the radiation or the visible light that hits its surface. Io is still quite bright with an albedo of 0.63, but you know, it's made of other compounds, and its yellow color is due largely to sulfur type compounds. Another big difference is that Enceladus is not very dense. It's only 1.6 grams per cubic centimeter, and water itself is 1 gram per cubic centimeter. And this sort of gives us a clue that its composition is very, very water-like, whereas Io has a much higher density. It's a couple of grams per cubic centimeter less dense than the Earth. So it probably doesn't have a big nickel iron core like the Earth does, but still, you know, it's made primarily from rock. So these two beauties are both very geologically active. And one of the most exciting things that I remember from these missions is when they discovered that there were active volcanoes on Io. And this was not discovered until Voyager 1 was actually leaving the system, because it didn't see really, you know, these weren't picked up until the features were backlit. And so Linda Morabito at JPL noticed this sort of plume coming off the edge, and she also noticed this bright spot at the terminator. And there's a lot of subsequent analysis of the images that showed that there were actually many active volcanoes on Io. And then in 2005, Cassini discovered that there were active cryovolcanoes, or geysers, or whatever you want to call them, that were happening on Enceladus. And these cryovolcanoes are constantly spewing material off of the moon and replenishing the E ring of Saturn. And so here we have a view of Enceladus. It's that little tiny dark dot there. And then you have all this bright stuff, which is the material coming off of, you know, shooting off of Enceladus. And this is the E ring. And the only way the spacecraft could really get this was to be in the shadow of Saturn, because this E ring is quite faint. So if you look at all of these rings of Saturn, this is actually, this diffuse one right out here is the E ring. And without Enceladus constantly spewing this out, this ring would probably, you know, disappear in fairly short order. So now the other thing about them is that they both have very young surfaces due to all of this activity. And when you look on Enceladus, up in the northern hemisphere, you do see some craters, but they're almost absent down here in the southern part. And there's also a lot of interesting features down here that suggest geological activity. Now it's even more extreme for Io, because, you know, it has all of these features, but not a single one really looks like an impact crater. So that surface is being turned over so fast, even faster than the surface of our planet, because we do find impact craters, you know, on Earth. So by contrast, we've got Mercury and the Moon and what they look like. And they're, you know, on this, they're roughly equivalent to Io in size. So when you have an old surface, this is the, you know, the number of craters you might expect to see. And this is because the interiors of these guys are, you know, they've cooled down and they can no longer really sustain that surface geological activity. So that begs the question, what is powering all of this geological activity on both of these moons? And the answer has to do with orbital resonances and the eccentricity of their orbits, as well as how close they are to their parent bodies. So this little animation here shows Io, and it goes around twice as fast as Europa. So you see they meet up always here, and it goes around 4 times faster than Ganymede. So what this sets up is this sort of a resonance where every time they meet up, Europa or Ganymede give a little pull on Io to sort of distort its orbit to make it a little bit more eccentric. And so that's the first step in why we get all the heating. So the second thing is when it always has the same face pointed towards Jupiter. And as it goes around in its elliptical orbit, which is highly, this is really not to scale, and the eccentricity is, pretty much, you couldn't see it by eye, but it is there. And so as it goes around once every 1.8 days, when it is closer to Jupiter, this side of the moon experiences more gravitational pull than this side, and the difference is greater than when it's further away. So this causes a flexing. And then the other thing is, because the orbit is elliptical, as Io is rotating, this spot right here is not always pointed directly at Jupiter. And this sort of causes a flexing of the sort of a torque or a twisting within the moon. And both this flexing and this twisting causes friction within the rocks, and that's what generates the heat that's driving all of this volcanism. And the same thing is true of Enceladus. It also rotates once per revolution, always having the same side towards Saturn. And it's actually even closer to Saturn than Io is. And it has a similar sort of orbital resonance, which keeps it in an eccentric orbit. So you see the eccentricity isn't huge, but it's enough to cause this tidal flexing. So as I mentioned, Enceladus isn't very dense. So what they think is that it has a shell of ice on the surface, and then under this it has a liquid ocean, and then it has a rocky core. And it's thought that this rocky core is somewhat porous and that water can percolate down into it. And this isn't a stretch, because the exact same thing happens on Earth. And so you get all this flexing, and the rocks are rubbing together, generating heat, and then the water percolates down in, and then it's heated. And then it comes out in these plumes of hot water that rise to the surface. And these are thought to be analogous to the types of plumes that we have on Earth that cause things like like Hawaii. So there's a hot plume of magma, sitting under the surface there, and it's coming up through the mantle somehow and heating that area and causing all of that activity. So the biggest hotspot in Enceladus appears to be down at the southern pole, because that's where these jets of water vapor and material are spewing out. So Io has magma, and it doesn't have much water at all. It's more dense, obviously, and they really don't have a good idea on what the interior of Io might look like. It's thought to have a core and a mantle, just like Earth, and then a lithosphere. This would be the crust, with the asthenosphere just underneath, which together actually form the outer layer of the Earth. And so the models, there's 4 different models. One is that the melting happens in the mantle, and in the other cases it happens in the asthenosphere. And they don't know if there's like a giant molten layer underneath the crust, or whether there's just pockets or what. But in order to try to figure this out, what they want to do is fly another spacecraft by, and they hope that using magnetism. They can kind of try to figure out what's going on in the inside of Io, but that's something that's you know, going to have to be for a future mission. So the volcanoes of Io are like, they're literally all over the place, and they're incredibly colorful. There's a lot of you know, there's a lot of vents here that you can see. There's a lot of lava flows, and it just is a, you know, I'm just always struck by the beauty of this landscape. So, you know, if you were flying by Earth and, you know, had a spacecraft flying by Earth, and you had a, you know, a space probe looking down, there's no way you're going to see a plume like this coming off Earth. And there's two reasons for that. One is that Earth is bigger, so relative, you know, so any plume that does happen relative to the, you know, size of the planet's going to be smaller. The other thing is that the atmosphere is very thin, so there's really not much to, you know, in the way of atmosphere to slow down the plume. And probably the biggest reason for these large plumes is that the gravity is so much less. So it's only about 18% of that on Earth. So the plumes are able to shoot up much higher than they do on Earth. So this one here from Pillen is about 140 kilometers high, and this is 3 times higher than anything we've ever seen on Earth. And over here, this one is erupting as well. And this dark spot right here is actually the shadow of the plume that's coming off that one. So you could see that at any time there's, you know, it's not just one volcano that's going off on Io. And this infrared image, which was taken by the Juno spacecraft, actually shows how active the planet really is. And here's the nighttime hemisphere, and you can see all of these spots all over the place. This little circle shows one that's, you know, brand new. And this data suggests that about 150 of the 400 or so volcanoes that are on the moon are active at any one time. Now, the other amazing thing about these volcanoes is that some of them are incredibly massive. This lava flow here is the longest in the solar system. So this is the active flow region, and these are various zones where the lava's, you know, breaking through. These are some other volcanoes that you see here, and the length of this flow is about 300 kilometers. And the colder parts of the flow here may actually be about 20 years older than these newer areas, because the Voyager saw this volcano erupting when it flew past. And the other thing that's amazing about this is the amount of area that it covers. It's about 620 kilometers, square kilometers that it covered in about 5 months. And Earth's most active volcanoes like Kilauea, it only covers about 10 kilometers, 10 square kilometers in the same period of time. So that's another reason why the surface is so incredibly young. You get so many very large active lava flows. And here's just a couple of pictures showing how gorgeous the surface looks. This one over here shows, this is a volcanic vent, and this is actually an overlay of the infrared image. So it wouldn't really look like this, but that's just showing you that, you know, there's really hot lava sitting right there. And here's a couple other vents. And then over here, this is actually a color enhanced view of Colin Patera. And it really gives you an indication of how complex the chemistry is around these volcanoes, because, you know, if it wasn't complex, then we wouldn't expect to see, you know, so many differences in the hues that are visible. Now, the other interesting thing is, as I mentioned, is sulfur, which gives a lot of this color to Io. Also, when I said it's spewing things into space, sulfur dioxide and all these sulfur compounds are actually going out and forming, rings, part of the ring system around Jupiter. So the Prometheus vent is actually really hot, and it's showing up in the near infrared here. And in the near infrared, the sulfur dioxide is dark, so you could see a circle of sulfur dioxide snow that's circling the vent. And here at this wavelength, it's bright, and so you can see that circle, and you see all the sulfur dioxide snow all over the place. And then here we have a mosaic in a variety of colors, and you can see all of the different colors that are present there due to different kinds of sulfur compounds. So here's another one, and this one's massive, and it's surrounded by a 1,300 kilometer diameter ring of this reddish sulfur material. And so this false color shows the vent here in red, and the temperature of this vent is thought to be over 1,000 degrees. So very hot. This is, there's no way that this is cryovolcanism. And when here we have an image of the same region. This was in April of 1997. And you could see that in September of that same year, we have a brand new volcano, brand new vent here, and material coming out just to the right. And then a couple of years later, you could see how much, both the central areas changed and this secondary volcano. So this is a high resolution composite of the side facing away from Jupiter. And it was taken by the Galileo spacecraft in 1996. And, this is one of my favorite pictures of all time. So I'll just let you stare at that for a little bit.
Ooh, very nice.
So moving on from, So as I mentioned, it was for a geology class, so I had to throw in some technical stuff, but I'll just quickly say that, if you've got volcanoes at the bottom of the ocean or in Hawaii, they tend to throw out hot lava down at this end, more of a basalt, whereas the volcanoes like Mount St. Helens are spewing out this kind of material. And you can tell what kind of rock a volcano is spewing out by the temperature. And so when the Cassini went by, it actually used its infrared cameras to get an idea of what the temperature was. And it took 3 readings in 3 different calderas, and it got these 3 different values. And this is sort of the error range. So, it's not a really accurate measure, but what it does tell us is that it's likely that these rocks are very similar to, these magmas are quite similar to the magmas that we have on Earth, as they're melting in sort of the same temperature ranges. Now, I don't want to leave you with the impression that Io is just about volcanoes, because it also has other features that are phenomenal, such as mountains here. So this is a thrust fault mountain due to sort of crustal movements. And there's several other mountains on Io that are actually bigger from the base to the peak than anything that we have on Earth. So now let's turn to little Enceladus, and it's actually getting smaller all the time because it's losing about 300 kilometers of mass every second due to these jets here. And the speed of the jet when it first leaves the crack is phenomenal. It's over 6,000 kilometers an hour. So the main constituent of the jet is water, mostly in the form of vapor. And in this particular case, the reason we can see these lovely jets is because Enceladus is lit up. It's kind of like Earthshine on the moon, the reason we see Enceladus is because of reflection off Saturn, and these jets are backlit by the sun. And all of the jets that have been seen are found down near the southern pole of the moon. These jets are seen to come from these tiger stripes, and this is a somewhat color enhanced view showing these stripes. And they measured the temperature of, can't remember how they did that, but each square sort of represents how the spacecraft measured the temperature as it was going across. And as you can see, the temperature increases as you get towards these tiger stripes. Now, this is still really cold. This is in Kelvin. So right here, the hottest one is still at minus 180 degrees Celsius. But you have to remember that this is over a fairly large area. So it's very likely that the temperature right down here in this crack where the jets are coming from is much warmer than this. But it's far cooler than what we see on Io. And that, further indication that these are cryovolcanoes involving largely water. And here's some close-up views. This is the Baghdad sulcus tiger stripe, and this segment is about 16 kilometers long. And here is, this one is actually a computer-generated image with a 10 times relief exaggeration to sort of show the structure of one of these tiger stripes with some, emphasis. And these are the cracks through which all of this material is spewing. And as you can see, it's quite tortured terrain. And when you look at Enceladus as a whole, it's got, it's fairly flat in terms of its relief, but it does have a lot of interesting terrain. It has an older region here to the bottom, and you can tell that because there's impact craters, and there's far fewer up here in this region. The other thing you can see is all of these sorts of stripes or striations, and here we have a crack, and it's going through all of this stuff. That suggests that this crack is quite recent. And the other thing to note is that all of these craters appear quite soft-edged. And this is likely because of all the snowfall that's happening due to the material that's spewing out of these cryovolcanoes. Now, the Cassini flew through a jet in 2008 and again in 2015, and it measured the mass of the constituents in the jet using its mass spectrometer. And what it was able to see in 2015 was molecular hydrogen, which, that's a very light thing. It only has a mass of 2. But it did find that there was a lot of water vapor. But interestingly, they also found methane, which we normally think of as an organic compound. And, on Earth, oftentimes it's generated by, the decay of living things. But there are other ways in which methane can be generated. And there's also carbon monoxide and simple organics, plus carbon dioxide and other more complex organics. So we're seeing sort of all of the elements that, or most of the elements that one would require for life coming out in these jets. Now, as I mentioned, although a lot of our methane was formed from living organisms, there are also ways to produce it through chemical processes. So the rock that is down in the, the floor of the ocean has a lot of olivine in it. And when water percolates in there, it goes through a bunch of reactions, producing a bunch of different types of rock and releasing hydrogen. And when this hydrogen gas, actually when it encounters carbonate rocks, it can react to form methane. So this is an inorganic source of methane. And the interesting thing about these compounds is that there are bacteria. These are single-celled organisms, so bacteria and archaea, which is a sort of another single-celled organism that tends to live, a lot of them live in extreme environments. And they can actually use organic molecules for energy, things like hydrogen gas, hydrogen sulfide, or methane to generate energy. So there's absolutely no need for solar radiation to maintain these living things. And we do see exactly the same thing on Earth, particularly at the divergent oceanic plate boundaries, that, like the ones that are running down the entire center of the Atlantic Ocean. And there are also some in the Pacific and, you know, all around the oceans of Earth, really. And these generate these molecules, hydrogen and methane. And what happens is the water goes in, it gets heated, and then it comes out, and it has a lot of dissolved chemicals in it. And we have, these ones are called black smokers, because you see it's all this black muck that's coming out. But there's also others that are called white smokers. And really, this is from iron sulfates that turn it black. And what you see here all over the place are tube worms. And these tube worms they don't actually even have a stomach. What they do is they have bacteria and archaea living inside of them, these single-celled organisms that live off of these organic molecules. And so it's sort of providing a home for these bacteria, and they are breaking down these compounds and generating energy in this process called chemosynthesis, as opposed to, say, photosynthesis. And it's these chemicals and the energy that these are generating that's driving this entire ecosystem down here. And in addition to these giant tube worms, there's also feather worms and mussels and vent crabs, and then there's fish that come down here and, you know, consume these things as well. So here we have an entire ecosystem that's not dependent on the sun. So Enceladus probably has something in common with, you know, these systems on Earth, because it has a nice crust above this active core. And, you know, as I mentioned, there was hydrogen and methane and other organics found in these jets. And that really does suggest that we have these undersea volcanism going on. And there may, in fact, be hydrothermal vents on the ocean floor of Enceladus. And so if these vents are providing what we need, all the things we need for life on Earth, then there's no reason to think that they might not be doing the same thing on Enceladus. So it's hoped with future missions that maybe they can, do a better assessment of the material coming out of here to see if there's compounds in here that would, be indicative of the presence of living things. So obviously a lot of what we consider organic compounds can also be formed abiotically, but some of the really complex things obviously cannot. So that's kind of what they're hoping to find in future missions. And I think we'll leave that one behind. And so I'll wrap up by with my conclusions here. Basically, both moons are much hotter than we would expect due to the tidal forces that flex and twist them, generating all the heat to drive this geological activity. They both have very young surfaces. Io is the youngest sort of surface in the solar system. It has obliterated all of its craters, and it looks like the volcanoes on Io are basaltic, so there's kind of like the volcanoes on Hawaii, but they're much richer in sulfur compounds and sulfur dioxide than most of our volcanoes on Earth, which is why it has this beautiful yellow color. Enceladus, on the other hand, expels primarily high velocity water vapor mixed with a cocktail of hydrogen, methane, and other organics. And so because of that, we think that the subsurface ocean of Enceladus may be an environment that could have the right conditions for life. However, I don't hold up much hope for Io because it sort of has this waterless surface that is quite cold. It has virtually no atmosphere, and then it has blazing hot volcanoes. So there's not much there that gives me much hope for there being any kind of life whatsoever on Io. Only time will tell. And so I just wanted to leave this up for a minute because this is, in addition to the NASA and JPL sites, I used all of these other sites to obtain information. And I also looked at some primary research papers that are shown on the bottom for some of this information as well. So that's all I have for tonight. And so I guess if we can, I'd be happy to answer any questions you might have, if we can turn on everybody's microphones.
Everyone has
Happy
the
to do
ability
that.
to unmute themselves as of now.
Thank you, Lori. That was excellent. I
Oh,
know
thank you.
we've done some, Kevin and I did a class with Mike Brown's through Corsica or Coursera, and a lot of talk was about Enceladus. So that would be interesting to see what missions they have going forward.
Yeah,
Any-
definitely.
Yeah. Does anybody have any questions for Lori?
Why didn't you include Europa in your discussions? Because its surface is extremely active and it is resurfaced regularly, also as the result of water. It has fissures that open.
Pretty much just because I didn't want to make it too long. Yeah, there's no other reason than just to try to keep it to a reasonable number of slides and, aim for a 40-minute presentation.
Okay, it was marvelous. Thank you.
Yeah.
You're welcome.
So Kevin has a question. When there's a probe being proposed to be built for Saturn, and now that I think of it, it's not going to Enceladus, it's probably going to Europa. So my whole question is null and void. Thank you very much.
Yeah, well, Europa is another potential, it is definitely an interesting body. It's not as hot as Io, obviously, because it's further out. So the thermal heating that it gets from the tidal forces is not as extreme, which is why it's not a raging volcanic ball like Io, but it's thought that it has a large subsurface ocean due to that tidal heating. So that, again, is another potential site for life. It doesn't have the same indications as Enceladus because it doesn't have these plumes that a spacecraft has flown through that, where the compounds that are there can be measured. So I think it's going to be a little bit harder to figure out, what's going on in Europa. With Enceladus, if you have a sophisticated enough instrument, you could fly, right through that plume and collect enough material to do a lot of really complicated analysis without having to land and drill or do anything like that.
Mm-hmm. Excellent. Okay,
That
anybody
was an
have any?
awesome, I just wanted to say that's an awesome presentation. Thank you, Lori.
Oh, you're welcome.
Europa's ice layer is also extremely thick compared to Enceladus. So the idea of having to go down 80 or 100 kilometers before you would actually hit liquid water is a bit daunting.
Yeah, try to get a small probe to do something like that.
there any other questions for Lori? Thank you again, Lori. That was awesome.
You're
Kevin
welcome.
has a poll, not a 30-second poll, but a poll that everybody he would like to.
We've never tried this, so this is some audience participation. So we are going to run this poll. Please make your choice, and we'll let it run for about 30 seconds.
Poll is closed.
Okay, I didn't do that. Let's do that again. Why is there a time limit on it? Well, you learn something new every day. I guess it's the quick and the dead. So you're either quick and vote or you're toast. There, that only went for about 12 seconds. Okay, we'll let that run as it is.
Oh,
We're going to
50-50.
share the results, and the answer is dead tie, 9 and 9. And next
That
time
doesn't
we
make
do,
sense.
well, not everybody had a chance to vote.
I
But,
misclicked.
we'll learn from this experience and try something for the next time. Thank you very much.
Enceladus really won. I misclicked.
Awesome. That is great. Thanks again, Lori.
Oh, you're welcome.
Okay, next up we have Malcolm Park, HD2's Polar Drift Alignment Tool demo.
Well, okay. I actually recorded a session. I screen recorded my AnyDesk, if you're familiar with AnyDesk. But what I'm doing is a polar alignment refinement using PhD2. So if you're an astrophotographer and you have a guide camera, that's what we would use for this scenario. I recorded this a few weeks ago, thinking at the time perhaps I could do this live at the meeting, and I made the recording just in case the weather was poor. But what I actually, I'm glad I made the recording because I wasn't thinking daylight savings. It's not dark. So I have no choice but to share this recording. So I'm just going to bring my screen on. And so hopefully we're looking at, what do you see?
We see your desktop. Before that, we saw your video player up.
And do you see the video player now?
We see the video player now, yes.
Okay, so I just wanted to show you this. This is the setup. There's a guide camera on the top. It's a Starshoot auto guider. Focal length of the scope is 175 millimeters. And you can see I've still got my polar borescope installed. And in a permanent installation, it's unlikely that that's going to always be there. And in my case, I did recently take that out because I ran my cables in through there up to the top. So it was because I did that I wanted a way to refine my polar alignment beyond just what you see with the reticle in the borescope. So in the past, I would use PemPro. I use PemPro to measure the periodic error in my mount and correct for that. But there's also a polar alignment routine in PemPro, which I would have used if I didn't have PhD, and I thought I would try PhD. So this is a video capture of my desktop computer. So I'm connecting remotely using AnyDesk to my set up out in the observatory, and I'm now launching PhD, and I've got PhD is now starting the polar drift alignment routine. And basically you just select it from the menu, you click start, and you select a star. And I haven't figured that out yet on screen, but I will in a second. So there, I've realized that I have to select the star, and when you click start, it disables the guiding aspect of it, and it just measures where it's drifting. And that red line and the circle are very important, because before I started this, I put myself intentionally out of polar alignment slightly. And so the line is going to tell me the direction in which I need to move that selected star in the green box. And the circle is the destination that I want to put that star at the center of. So it runs for a little while, and then it settles down. And once you've decided it's settled to your satisfaction, then you go to your mount and you move your alt azimuth controls physically. And meanwhile, the PhD 2 is still taking pictures, so you can see the star. I'm moving it towards that circle. And in this case, I decided, because I moved it a little bit off polar alignment, to move both axes, just to make sure that I got it as well centered as I could. So we'll just let that finish. And of course, you always move it the wrong way, and then you move it too far the wrong way, and then you have to move it back. But at the end of the process, you should have a nicely polar aligned mount. So at this point, you would say, okay, yeah, I think that's well centered, and I'm going to run the routine again. So this time, what you want to see when you rerun the drift alignment is that the red circle and the line will basically the red circle will return to that star eventually. So we'll rerun it. Doesn't matter what star you pick, but it bounces around a little bit, and so I'm not touching the mount at this point. This is just the software now is measuring the periodic error, and it's pretty much, not periodic error, polar alignment error, and it's really just settling, and there we go. So at this point, I felt comfortable that was a well polar aligned position, and that was the end. So if you're a user of PhD, and you might not know about this particular feature, I hope that's useful to you.
All right. Thank you
Okay.
very much.
Thank you, Malcolm. Any questions? We'll have to
Wow.
come over and see it in real life sometime.
I have another poll.
Oh. Okay.
No more questions. Let's try another poll. There we go.
We're aligned now.
And I have no idea of the time.
It's up at the top.
No, but I have no control over it. I
Mm.
don't know why it stopped before, and I don't know. Anyway. We'll give it another few seconds here. Okay, so we're at 35 seconds. Can any of you see results at all?
Yeah.
Oh, okay. So I'll just end the poll now. And it says 55% looks great. I want to try it out.
And 45% say too scary.
No way, Jose.
I never
I just-
actually saw the poll. I still see Malcolm's screen, so.
That's probably Mark's internet non-service.
You may be on a bit of a delay there, Mark.
Yeah. And so
I like that the poll is anonymous. We don't have to admit who's too scared.
Oh, there it is. I've got it now. I got the results anyway. I definitely will give it a try.
So
Okay.
Malcolm, did you have to be pointed at the pole? Or were you pointed at the meridian, or where were you pointed?
Oh, yeah. So I'm sorry, I should have mentioned, yeah. One of the things that you have to do when you're using Pempro is you have to change your orientation and point down near the zero declination and just east of or west of the meridian. But with this, you're just pointing at the pole.
Okay.
Yeah. Like, so I literally unpark the mount and then run it from there with the mount connected and everything. But yeah, just straight pointed at the pole. It's very effective. I thought it was much simpler than the Pempro routine. And I'm sure there are others out there too. But
Okay. Any other questions? If not, we are going to thank you again, Malcolm. We're going to move on to Hank Bartlett and Hank Sunspot. You.
Now that's scary.
Hi, Hank.
Can't hear you.
unmute.
Hank is not muted. It's something to do with his local microphone or input on the
Nope, he
Zoom.
said just a minute.
Next month, we're going to get Hank to join early, and so we can work this through. Nope, still nothing. You're not muted in Zoom. You may have a different input in Zoom, or you may have.
I've tried all the.
There you go.
There you go.
All
There
right.
you go.
So for some reason, my headphones aren't working for the microphone. So
Oh.
I've switched to my camera. So we'll take this up out of the way. It usually does work, but something threw it off. Okay. So we're okay now, eh? Before I start saying anything about the sun, how do you vote on the poll?
I was running it, and I'm assuming that you just go and you click on something.
Well, assuming isn't doing, because I clicked on it, didn't see any difference. And
Okay.
like, is that what you do? You click on the line you want?
Yep, and then 20,
Okay.
20 people responded.
Yeah.
So,
I
And it
didn't
was
see
a-
anything until the results.
yeah, we're
I
not
got it.
talking to you, Mark.
Click on submit, otherwise the answer goes nowhere.
Yeah, because I was just sitting here and going, how do you vote? How do you vote? How do you vote? And nobody was answering me, so I figured I probably wasn't getting through. But yeah, I've never done one before, so I've never seen it. Okay, so we're going to go to share screen here. And there's my screen. And we're going to go to view full screen. And here we are at Hank's monthly sunspot, which is just going wild these days, of course. Yeah, right. Solar activity for March 10th to April 14th, which is we would call our meeting month, has had 7 active regions from 12,808 to 12,814. And a couple of them have been pretty good and pretty promising, but they went nowhere in the long run. March 11th, we had an X-ray baseline of 10 to the minus 7.5-ish about. The lowest after that, it went down to 10 to minus 8.1, which I certainly expected it would be going the other way in the ramping up towards solar maximum, but it didn't. And we end up today with about a 10 to the minus 7.4. So a very slight movement on the baseline. There has been activity higher, activity right up almost to the 10 to the minus 6, but those were very short flashes of eruptions in that. I managed to get out to 17 observing sessions. I did not get out today because grandsons come in more important and had them for the day. So I missed today's solar, but it didn't look like it was much anyway. This shows graphs of what the past month has been. The 11th in the upper left-hand corner there shows that baseline down around 10 to the minus 7.5, like I said, and a few peaks with the sunspots that came and went and active regions that came and went over the time. Into the final week in the lower right-hand corner here, the final day actually, yesterday and today, some good activity almost reaching sea level, as did the one above it. You can see there, number 2, almost reached sea flare activity, but not quite. In interesting points, on the 12th of March, this sunspot on the right-hand side there in the active region you can see on the left gave good promise with a nice dark solid spot that thought was going to erupt into something, but it did not have much active region around it or any facula and that or plage showing a lot of extra activity. It was just a good cool dark spot, and that was about it because it moved away rather quickly. On the 19th of the month, there was this nice active region down in the lower right in the southwest, and I was imaging it and I thought something looks odd above that. Something looks odd, and I looked closer and closer and took my time, and this has been brought out, this brighter region that almost appeared as a twin to the lower one. And these two prominences were just amazing because to the eye, they did, like I say, almost appear as twins. Almost as if I thought at first it was a reflection of some sort with the two etalons. But of course it wasn't. And here, when I did a little dodging and burning, came up this beautiful, much more beautiful than the front one, this active region or prominence. And a lot of activity around it. So that was really cool. I learned a little bit more at that point about dodging a little earlier and not going for bright, hard detailing as much, which brought out, like I say, the softer elements of the dimmer prominence. Now, then on the 22nd, we had 2 sunspots come on. We had 10 was kind of just past midway, and 8:11 and 8:12 came on pretty close together and had a decent number of spots, especially in 8:11. 8:12 had a little larger, darker spot, and both of them had quite a bit of plage and facula around it. You know, it was looking really good and it was getting a little bit of activity, but again, it faltered and we just can't seem to kickstart anything that is going to bring the solar X-ray average or baseline up enough and get activity really rolling. On the 30th of March, we have this beautiful prominence in the northwest of the sun where 12 and 11 are now starting to work their way off, or 11 is starting to work its way off. And as you can see on the right-hand side, active region 811 is showing some plage and even a little bit, tiny bit of flexus spot activity, but the 812 is pretty well disappeared. There's very little that actually showed up, nothing evident here in this image. So it was dying out just the same before even its predecessor. On the 6th of April, this image on the left was these are both the same image. The image on the left is where I took that same standard detailing before dodging that I've been doing. And I looked at it, and after I posted it even, I wasn't satisfied with it. It just seemed that there was more in my mind there than what was showing. So I went back to the base image and started doing some dodging. And as you can see in the southwest especially, even more than up in the northeast, a great deal more prominence than what I have in the first image on the left. So it's something I've got to get in the habit of doing. And also in the southeast, you can see prominences appearing that otherwise didn't in my first image. So I've got to do more dodging at the beginning and lightening the background prominences and then going into the detailing. So I'm hoping to get in the habit of modifying it in this way and processing it in this way. This on the 8th was absolutely beautiful in the eyepiece. This can't possibly show this amazingly nice dark filament. And for those that might not know, filament prominence, same thing. The difference is the filament is laying over the surface of the sun to our view, and the prominence is cascading out into space, and it's all in the same. And this, on the right-hand side, if we go there, this filament lifting, this filament, filiprom, I called it on Facebook where I posted it, is lifting up. And why there is a break, I don't know, near the horizon of the sun, the limb, but there is. And then in some of the images I saw that people took with ASI cameras and all that, this goes straight up and then loops backwards. And what you see rising is actually what's falling behind and going back down. So this was an incredibly, if we'd seen it from the other perspective, from the side, it would have been an incredibly big loop that was rising up. I have no idea, but that is about, that rise there is about 200,000 kilometers above, 2 to 250,000 kilometers above the surface probably. And if you add it all up, you're talking, right, maybe 500,000, close to 1 million kilometers, because this was absolutely amazing. And the filament itself being so dark and dense was what really caught my eye. And I started looking at it, and then I saw this light prominence coming up. So started imaging it, and I put on the extra Barlow and zoomed in on it. So this is the left-hand side is a 1.5 times Barlow. The right-hand side is the 1.5 plus the 2 times to make 3. And it brought it up rather well, but you do lose some detail in doing so on the filament. It's not, doesn't look as 3D as it did, but it was fantastic to watch that. And it did end up collapsing and bursting away both. It fell back in and also went out into space. It would have been really interesting to watch that, but you'd have to, well, either watch the Gong H alpha or sit there all day long or run a camera all day long. But it was really nice, yeah.
Just got a question. When you're doing this enhancement, you see that, feature, that arc along the limb of the sun. Is that actually the chromosphere that you're bringing out?
You mean now, is that on the left-hand side picture or?
Well, just this
or the,
sort
or
of,
the, this whole big one, the big
no,
prominence?
the
Yeah.
arc that's running along the edge of the,
On the right there, yeah. Oh,
No.
I see. Oh, all the way around, all the way
all
around.
the way around. Is that?
I would suppose so. I don't really know. It comes up that way. There's always that darker glow right along the edge. And that, of course, is the most active region
Mhm.
because all the activity, the broiling and everything is right on the surface. And you're looking at that, in my opinion, from the side, just like you would be if you're looking at a planetary nebula. You look at a planetary nebula, just like looking at a balloon, you can see through the main part of it. But at the edge, where you're catching a cross view of all the activity, it becomes much more dense. So chromosphere, I don't know. I can't actually answer that technically, but it is always there. It gets a little darker with the enhancement, but it's your guess as good as mine. I could dig into that and try and find out, but it should be that region for sure. That's all I can say on that. On the 10th, it was really cloudy, but there was a little bit of break in the cloud, a little bit of thinning in the cloud, I should say, more than the break. And I managed to get out, and I was absolutely amazed at what I caught of the solar surface when the cloud level, which of course, as I've said before, the clouds are made of hydrogen, and hydrogen is what we're imaging. So therefore, it all shows up and it's red. And normally I can back that out of there because it's about 1/4 to 1/10, depending on the day of depth and this, I could not get rid of the red this time, but still was able to penetrate that and actually get the detail that is shown here of the prominences and the activity and filaments that are on the surface. And that was quite surprising. And actually, it gave a little better surface rendering with the extra humidity or hydrogen in front of the sun. And I found that before where the granularity is a little more evened out. So I wasn't ashamed or anything of the fact that it's got a red sky. And this is yesterday. This is my last imaging of the month. And I did not, like I say, did not get out today. This is AR12-814 and a very decent looking sunspot. From what I see, it was bigger today and had more tiny little spots trailing towards the west from the upper dark region, and a little bit of decent prominence around it in that. But that's basically it for the month. We have gone pretty well everywhere but nowhere, and it's not ramping up at all yet. And I sure hope that next month we have a little more to report on it being more active. That's it for me.
Those are awfully good, Hank.
Thank you all for listening. And
Kevin here. Hank, where can people find your images?
well, I post every day on our Facebook page and the RASC Facebook. I know there's a lot of people who don't want to go on there, but just channel it and only pick that as that's it, and don't go to anything else. You know, I could post them other places. I don't know whether is it any easier to post on the RASC site anymore on our, because I know a few years back it was kind of difficult to do that.
That's a darn good question, which we will take a look at.
I'll take a look at it, but you're welcome to look at them on there. And I hesitate to send them an email because I don't want to plague everybody with daily images on the email. Thank you very much.
Oh, yes, Hank, there was a lot of H-alpha activity today.
Yeah, I kind of figured there would be, considering I was tied up for the afternoon especially.
And yes, the sunspot is getting bigger.
Yeah,
Yep.
and this is what we want, Kim, is
Yes.
we want it to get bigger and bigger and more active and have a couple more come behind it.
Yes.
So, yeah,
Yeah.
all right.
Okay, is there any other questions for Hank? If not, Kevin has, oh, John, yep, Don, unmute. Unmute. You have to unmute. There you
There.
go.
Thank you. Hey, amazing pictures.
Thank you.
Congratulations.
Thank you.
Very impressive. One of the things on your graphs, I was asking, what is the Y scale? It looks like you're measuring watts per meter squared.
Yes.
Is that sun's output, or what is that measurement?
That's the X-ray output of the activity on the sun.
And how do you measure that?
I have no idea. It's a GOES satellite, the SDO satellites and that. It's them, and this website I go to just
it pops it up for you.
Yeah, it pops it up. It's called Sun Today, and it's out of Russia actually. I prefer it because it only does one line, where the NOAA does both short and long, and the long seems to show more of the actual activity. So I use that as a very simple watch, and I check it multiple times a day. And now I noticed that Kim mentioned this week something about a site that will let you know if there's any activity or if activity is peaking, because by gosh, sometimes that slowly ramps up over a long time. But then there are times, and I remember a few years back, Kevin emailed me or texted me on my phone and said, there's an X 1.9 right now. And I went to the computer and bang, it was almost right off the chart. And I grabbed the scope, went outside with it, and you've got to be there at those moments. And they're hard to keep an eye on unless you're watching constantly. Okay.
Sure.
All right.
Okay. Okay. Kevin, have another poll?
Kevin does. Let's see what happens. This gives everybody an opportunity to see what a poll is and how to answer it. And so far there's 0 votes. And there's still 0 votes. And we have 1 vote. Okay, somebody has figured out how to do this. Now 5, 7, 9, 10, 11, 12. And while we're talking about that, I just got an alert, KP index of 4. 4.
I'm not voting here.
Okay.
Is that the Kingston Cloud Index?
I don't know what to click on. Oh,
Okay.
Click on the line.
We'll
just
give
click
you-
on Hank's got too much time on his hands.
We'll give you five more seconds. 3, 2, 1. Thank you very much. And I share the results. Does that show up?
I see it.
Okay. You're different though.
And
You're
Now it's gone.
okay.
Hank's solar spotlight is what got the most votes.
Yeah.
No,
Okay.
now it's Hank's got too much time on his hands.
No, that was a second run. It's very
That was me that clicked. Hank's got too much time in his hands.
the poll relaunched itself automatically, and I did not do that. Okay.
Okay. Awesome. Thank you so much, Hank. Well, we can only hope that things will actually start ramping up, since we're supposed to be up the upswing of 25 here. So let's hope the next month produces some sunspots. Okay, next we have Rick Wagner, who's going to do What's Up in the Sky.
Okay. Okay, the sky this month. April. Events on the ground. We start with, looks like Queen's seminars and stuff is shut down probably for the summer. We'll get back into those in September. 23rd and 24th of April are BAA webinars, the radio astronomy section, and then their spring webinars to replace their spring meeting. 24th of April, also an AAVSO webinar with Dr. Boris Gainsika, the end of the worlds. I'm not sure what that means. Then a week later, another AAVSO webinar on how to start with CCD photometry. On the 12th of May, the BAA is having a Schwarzman-Wachmann webinar. And I noticed the other day that the Queen's Observatory, Fast Radio Burst podcasts, they've got another couple of versions, issues, though, Judith Irwin, and then another one on future missions ingenuity. So you should go to look at those. They're quite good. The dark sky viewing areas are both closed because of COVID. Our lighting conditions are looking awful. You can see we've got an awful lot of daytime, over 14 hours of sun in the sky. We're down to only about 6 hours by the end of this month, only 6 hours of astronomical darkness. Sun is getting higher, 55 degrees, 59, 61 by early next month. So the solar imagers are going to get better and better seeing, presumably. Sky events, 20th of April, first quarter moon. On the 22nd of April, we have the Lyrid meteor shower. It's not a great one, but usually sort of 15-ish meteors per hour. And unfortunately, it's taking place very close to full moon. So your best bet is on the morning of the 22nd for an hour or two between moonset and the start of twilight. The 24th and 25th of April, Mercury and Venus are going to be close together, very low in the western sky shortly after sunset. 26th of April, full moon. 26th and 27th of April, Mars passing M35. So that'll be another photogenic opportunity. It's a smaller field this time. So anybody with sort of the 60 to 80 millimeter, 90 millimeter refractors and stuff can get a nice shot of M35 with Mars in the field of view. 3rd of May, last quarter moon. On the 4th of May, the moon will be below Saturn and Jupiter before dawn in the morning sky. Jupiter and Saturn are getting quite high. It's quite amazing. The other morning I woke up at 4ish or so, and there's this great big purple blob on the horizon, and it was Jupiter coming up, and Saturn was already well up. 5th of May, the Eta Aquariid meteor shower peaks. It's a southern shower, so it's not very good up here, but we do tend to get occasional earth grazers coming up from the south, so it can be quite spectacular. And that one is best before dawn on the 5th and 6th of May. 10th of May, International Astronomy Week begins. 11th of May, new moon. And 12th of May, also our meeting night, we're going to have some competition with some sky stuff. The moon will be 1 degree from Venus, with Mercury standing about 10 degrees above the pair. And then the following night, the moon will be about 1 degree or so from Mercury with Venus down below. So it should be very attractive in the twilight sky. Here's what the moon looks like for this month. You can see we've already passed new moon. So if you want deep sky, better get out there pretty quick. You got a couple more nights before the moon will be setting too late for convenience. Asteroids this month. I sent out an email about Hi'iaka occultation tomorrow night, and it looks like it's going to be clouded out. I went back to Dr. Swami, who asked for our input and got some additional information from her. And it's a whole different group. They have their own predictions website, and the reason they're separate is they're actually studying trans-Neptunian objects, centaurs, and Jupiter Trojans. So they're only looking at occultations by those kinds of bodies. So they generally tend to be much smaller, much fainter, much further away. So more difficult to observe. It's a cooperative effort from the Laboratoire d'études spatiales et d'instrumentation en astrophysique and the Observatoire de Paris. It turns out I obviously didn't read my email very carefully, but Hi'iaka is actually one of the moons of the trans-Neptunian object Haumea, which has 2 moons and rings. So this is why they were particularly interested in this occultation and why they wanted observations from way outside the path. Given that there are 2 moons and rings, the prediction of the exact location of the object and where occultations will occur is very difficult. And of course, with the rings, you might get occultation. You might be able to detect the rings even outside the path of the actual occultation. So it looks like it's going to be cloudy, but on the 19th of April, there's an even better opportunity for us. Aeneas is going to occult about a 13th magnitude star. But again, it's predicted to be cloudy. These are the charts that they produce. This is the Hi'iaka occultation. You can see we're sort of somewhere about 2 sigmas off the path. And this is the chart for the Aeneas occultation. And we're much closer to the path, but it's going to be a more difficult observation. It's only about 18 degrees above the southern horizon. And for me, it'll be in the trees, which will make it really tough. Mars and M35, you can see in the center is M35 with its little companion cluster beside it. And Mars goes by on this line here. On the 25th, it's nicely in the field. On the 26th is its closest in the evening, and then on the 27th also still in the field, but perhaps less attractive. Explore the Universe. We're trying to encourage people to do their Explore the Universe certificate. The early spring constellations are becoming more prevalent now, more easy to see earlier in the evening. Again, moon phases in the Maria are always available throughout the month. The planets, Mars is still in the evening sky with it going by the feet of Gemini. Its orbital motion is quite easy to see over a night or 2. And then Jupiter and Saturn are getting up quite nicely in the dawn sky. And that's all I have. Any questions?
Awesome, Rick. Awesome.
Thank you, Rick.
There you go.
Any questions for Rick? Everybody's going to get out there and observe. Won't be tonight because the cloud is rolled in. Oh, moon is now showing again. Okay, but
I
Rick,
see you promoting Explore the Universe.
yeah, definitely.
I noticed something out in the sky when I was out the other night. That was the mosquitoes.
I haven't seen one yet.
Oh,
Oh yeah, I was.
they're out.
Go out in the dark.
They are out. Okay, now Rick is going to carry on with the Leaside Observatory and the Boltwood Telescope.
Okay. So I'm going to focus this time on the observatory itself, a little bit on the telescope. So this is the site I chose, well, that I was forced to choose. I had a much better site, but I was informed that I would be shut down because it was too close to the water. So you can see I built it here in the trees, which, thinking back, seems less than ideal. I did take down a couple of trees to make room for the roll-off roof. So the first thing you have to do is you have to dig a hole. So this was about 4.5 feet square and 4 feet deep, down maybe 4.5 feet, except where it hit bedrock. You can see a big shelf of granite. And what I did in there was to try and hold the concrete pier to the bedrock better, I drilled holes into the bedrock and then epoxy loops of rebar that you can see on the left. And that way the concrete pier locks onto those and won't tend to shift around. Unfortunately, you find that the frogs jump around in the dark. They can't see the hole, so they fall in. Every morning I have 5 or 6 frogs in there that I had to pull out and rescue. So here's the materials for the pier: 150 bags of stone mix, and the mixer in the background that I borrowed from a neighbor, thank God. So pour a bag in, pour in some water, let it mix, empty, and repeat, and repeat, and repeat. Poured it all in by sand or by bucket. You can see the rebar that's in there. I didn't use any forms. That was one of the advantages to doing it myself rather than having a truck come in, was I didn't have to do a proper job of building adequate forms. So once I poured the pad, and the pad is probably almost 2 feet thick. Then I built this concrete block pier on top of it. There's rebar extending up out of the pad into the bottom of this. Then you can see I have rebar running down all the corner holes. So I filled the corners of this block with concrete and rebar, and then poured a cap on top that you can see there with 1-inch bolts, 1-inch threaded rod embedded in it to take the pier. And then around that, I built a sloping form, tapered so that it gets fatter and fatter down below ground, and then filled all that with concrete. And then I backfilled everything and put on 4 inches of foam to help prevent heat loss. The heat tends to conduct up the pier, and so the ground tends to get colder under there and cause more freezing and stuff. So I put insulation around it to reduce that somewhat. And then I wrapped the pier also with styrofoam and covered the foam, so it's all looks nice and natural. So then I have to start the building. So that was 4 12-inch sonotubes, again down 4.5 feet. Fortunately, this whole area was almost entirely sand. I didn't run into a single rock, other than bedrock. I didn't run into a single rock in digging all the holes. And there's the sonotube. 4 of those filled with concrete, and then saddle plates on top of that. Then I had all the wood delivered to build the observatory. And of course, somehow they know how to pack it exactly upside down. So all the things you need first are on the bottom. All the things you need last are on the top. So I have to restack it all. The base of the building is 6x6 posts on the saddles. And then I notched the outside faces of the posts 1.5 inches. So the rim joists are actually sitting on those shelves. And then wrapped that again in another layer of 2x10 rim joist. So it's doubled all the way around. There you can see the inside rim joist sitting on the post. Here's a view underneath of the structure. It's all 2x10s on 16-inch centers. Everything is doubled around the opening for the pier. Exterior grade, tongue and groove, 5/8 inch decking, glued and screwed everywhere. Because it's exterior grade, I didn't do any painting, any messing around underneath. Plus the building is is up high enough that it's well ventilated underneath. You can see the open bay that's north of the pier, and that's going to be where my cables run over from the pier over to the wall. So then the walls are basically pretty much standard stud construction, 2x4s with a 4x4 running along the top of each side wall that's going to carry the roof. So there's the walls done. I took the ridge roof and screwed it in place and then hung a tarp over top of it to keep rain out of the interior for a while. It works quite well. I built the rail structure. So these are 4x4 posts. You can see at the bottom of the verticals, what I used is leveling jacks from scaffolding. So you drill an 1.25 inch hole up inside the 4x4 and put this on. It's just sitting on a 18x18 patio stone, and using the crank on here, you can adjust the rails up and down in case of any frost heave or anything, and keep the rails perfectly level and straight with the building. And the knee braces are all mortised and tenon glued and screwed in, so they're in there for the count. So then I had to move the pier in. I had it in the shop. Mark very kindly brought his van to help me get it from Stittsville and bring it into my shop. But I had to get it from the shop into the observatory, and the not having stairs yet, it was going to be a bit of a lift. So Brian Cooper from down the road brought his tractor down to carry it, and one of the other neighbors came along, Evan, to help. So you can see manhandling it out of the bucket into the building. The 2x4s on it, I just screwed on temporarily. And between the two of us, the pier weighs 350 pounds. And by lifting on the 2x4s the same way you would lift an anvil, the two of us quite handily lifted it up and plunked it on the pier with no strain at all. And amazingly, even got it on in the right direction. So the roof gets built in place. You can see this is in the foreground here is the top of the wall, and the roof sort of substructure lying on it in the back. And eventually it gets commercial weight garage door wheels and tracks, and that's what it runs off, which is nice because it can't lift. It's entirely fixed in place. It won't blow off. The roof is a 2x8 ridge beam, 2x6 rafters, and 2x4 purlins. You can see the aluminum and the eye hole in the center. I suddenly came up with the idea of fastening that in there, and I use it as a gantry. So I put a come along on the eye bolt, and then I can lift the pieces of the mount and roll the roof back and forth, so I can use that to install the mount. The other eye bolt you can see with pulleys. There's a total of 6 pulleys on 4 eye bolts, and that allows me to install the telescope, lift it on and off by myself. The telescope weighs almost 200 pounds, so that helps me do things when I'm alone. So you can see working on the roof, I spent a lot of time up there closer to the sky I was looking for. Sometimes lying on the roof. Basically 1x3 strapping every 8 or 9 inches. I can't remember. It's the same spacing as the ridges on the steel roof. So it's just steel roofing, and then the minimalist ridge line on it. I add flashing, carefully cut to pass the wheels of the roof and cut around the tracks and everything, and it leaves the biggest gaps to the outside are about 1/8 of an inch. So I never get any vermin or anything in. So then I was expecting to have to install the siding and do completion of everything following the winter. So I painted the exterior of it all to protect it through the winter. Then bringing the mount out. This is the declination axis. Here's the polar axis, and you can see the come along. So I'm able to just tie this strapping around it, crank it up, and then put it into place. Trying to get it all perfectly aligned to be able to get the bolts in the holes is kind of difficult. So it's nice to have, you know, the slow control of the come along. So there's the mount installed. So then I needed to put power. So I thought, well, I'll just dig a quick trench over to my shop. And well, by the time you do it to code, go down 3 feet for sand and more sand and 2x6, blah, blah, blah. It ends up actually that the ditch was actually larger in volume than the hole that I dug for the pier. But I dug it all, put in the proper armored cable. You put down 3 inches or 6 inches of sand, armored cable, 6 inches of sand, 2x6s on top for protection, warning tape, and then backfill it. And I put 20 amp service out there, and it seems to have been fine. So little finishing touches. You can see I painted the floor with a material called deck over, which I really recommend. It's like a rubberized coating with traction material in it, and it's protecting the wood beautifully, nice and you know, never gets slippery when it's wet or anything. It's really great. The aluminum flashing I bent and screwed on so that it covers the transition from the floor to the pier. So again, I've never had anything bigger than an ant inside the observatory. Here you can see the doors that I put on the cable bays. I cut the corners out a little bit for the cables to run down in and then come back out on the other end. You can see the cables are quite substantial. So on my old observatory, I used built-in vacuum cleaner piping, and I run a string through it. And then I could just pull any cables I needed, but the connectors Paul used on all his cables are all like DB25s and stuff, and it was going to require too large a pipe and too likely to have jam ups in the middle. So I put a little desk in the corner, a chair, the monitor is mounted on the wall. My SQM meter is on the wall. It can see the sky when the roof's open. Very nice feature is I have an power bar with each outlet is switched. Let's see what else. Put in a couple of shelves to store some books, binoculars, little pieces, wrenches, and stuff like that. The outriggers I've stained, and then I wrap them through the winter. I wrap them in a tarp to keep ice and snow off the rails and out of the garage door tracks. So here was the point of the whole exercise. This is the telescope finally installed and looking at the sky. Here it is when it's stowed. You can see my nice purple yoga mat that I wrapped around the counterweights. It's 100 pounds of counterweight, and you walk into that in the middle of the night and it literally drops you to your knees, the impact, without moving your target. So at least your guiding isn't ruined. Lighting inside, I have Christmas red LED rope light all the way around the inside of the building. And then I have 4 LED lights mounted on the walls. I painted the inside of the observatory a pale gray. My old observatory in Ottawa was black inside, which worked there because I had a lot more light pollution. But out here, I don't have the light pollution, and I find that the gray reflects the light around a lot more, so you get a lot more even lighting when you're working out there. Can't see anything else. So there's me with the telescope to give you some scale on how large the thing is. There's me with my beard and the telescope. This is the, I think this is the only thing I'm going to talk about on the telescope itself. This is the focuser, and it's a big sled on linear bearings running on precision steel rod. And then second set of steel rods just helps keeps everything square and stuff. And then the whole sled is driven up and down by a linear actuator. But it means that the camera is bolted in place. And so I can't rotate the camera to, say, find a guide star or to frame something better. You've probably seen some of my galaxy shots that if it's a big, long galaxy that's oriented east-west, I cut its tips off. This is the inside of the telescope. You can see Paul designed it fully baffled, so it's very dark in there. And this is the control panel that I built. It has in behind it 24, 20, 15, 12, and 5-volt power supplies. The Arduino that controls the focuser. All the switches and stuff to turn on the, there's heaters behind the primary and the secondary, fans in front of and behind the primary mirror. And then I have an on-off switch that turns on everything except the primary heat and the fan. The bottom switch here is a kill switch that kills power to everything. And I leave the primary heat and the rear fans on all the time so that it doesn't dew up. My old telescope in Ottawa, it would get cold at night while I was observing, and then the warm summer breezes would blow through and condense on the mirror, and it ate the coating off. So there it is, finished and in use. It's been 4.5 years or so since I got it running. And I've probably shot somewhere around 45,000 pictures with it. So I think Paul would be pleased that it's being used.
So Rick, every picture I see has all these trees in it.
Yeah.
Where is your...
I built it in the bush.
You have a clear view to the south?
Yes, it's at the north end of the clearing. And unfortunately, I mean, not being experienced with large trees much, when we moved in there, I looked at the sky and I thought, well, this looks satisfactory. And these are all fully grown mature trees. Well, I didn't realize, but fully grown mature trees do continue growing and they do fill in. So my sky is gradually getting smaller. However, I can still get probably 4 hours of observation on targets sort of from +10 declination to about +60. So while it's very restrictive, one always wants what one can't have. So there's invariably comets that are in the trees, occultations, whatever. But there's 150,000 aurora Lyrae stars, and 50,000 of them go through this part of the sky I can observe. So I'm enjoying it.
Awesome.
Thank you.
So Rick, there's 2 questions in the chat area.
Okay.
First one was from Peter Jedicke.
Yeah.
And why notch the 15 centimeter by 15 centimeter posts? Why not just set the joists on top of the posts?
I don't think the fastening, the joists wouldn't be very stable. Start my video. All right, here's my video. The joists sitting on top of a beam or a post, I don't think the joists would be as stable. So I preferred to have them lapped into the posts. It just makes for a much more sturdy fastening. Also, if you do get extreme winds tending to lift, it's much more solidly grounded that way.
And the second question is from Judy.
You're muted.
Okay, second question is from Judy. Why did you not put the roll-off roof posts on concrete tubes similar to the observatory? Would it not have negated the need to adjust these for levelness should there be any frost?
Yeah, that's a good question. The unfortunate thing is, in fact, you can see, I'll share my screen again. So you can see in this picture, beside the observatory is bedrock, and that bedrock extends all across there, and it's all on a slope, and it's just in such a position that I didn't think I could easily get concrete piers installed that would be stable and would stay in place, and so I just thought it would be easier just to make it adjustable. The history of the scope. That's I'll talk more about it next time, but it's a telescope that Paul Boltwood built in Ottawa, or had built for him. Mostly he designed it all, and it's anybody who knows Paul Boltwood knows that he was obsessive to the nth degree. So all the machining, for instance, is all ultra high precision, 10,000th of an inch machining. It's all stainless steel. If you look at the baffling inside the tube, if I go back there, yeah, you can see the spider is mounted on this big ring. And Paul told me when he gave me the scope, he said, these edges here are knife edge. And he's right. I've cut my arm on them because they're machined to, all the baffles are, when they say knife edge, they're like honed sharp. The secondary has offset vanes. A lot of people, the vanes are exactly radial. And that means the secondary can oscillate very easily, whereas this has them offset. And in order to do that and make sure that the vanes are exactly in front of each other, you have to machine the lengths of the vanes to a 10,000th of an inch. So anyway, so Paul built it. He bought the mount, the Mathis Instruments MI750 mount, and was working with a company that was interested in building mount controllers. And so they were debugging the mount controllers, and then unfortunately Paul got sick, and over a period of a year or two realized he was never going to have the mental acuity to finish the whole project and actually make use of the telescope. So he donated it to me. The mount, the pier, the telescope, and a QSI 8300 camera. So I'll talk more about it when I talk about the whole the telescope itself.
So I'll put you down for May then, right?
Okay.
Gonna have part 2.
That was easy. Let's try for June, July, August, September, October.
Yeah. We'll start showing some results from it.
Oh, yeah, that'd be great. Okay, excellent. Does anybody else have any questions for Rick?
I should mention that while we're talking, the telescope has started observing, and it's just
Good luck.
just finished its first exposure. Well, it's still clear here.
Oh, it's totally clouded now. Okay, well, I guess what I have. Who was that?
Sound like Mark?
No. Okay. Okay, so if there's no other questions, we will carry on for next month in May. Rick's going to give a talk on the Boltwood telescope, and Mark Cody is going to tell us about the light pollution endeavors in Peterborough, which they've been working on that for quite a while, and he's had great success. The virtual science rendezvous is on May 8th, and it's actually online this year. So it's at sciencerendezvous.ca as to what's going to happen. Oh, great. And our next meeting is May 12th. We are in contact with Belleville. They want to try to do a combined meeting, so we don't know if it's going to be May or June, and I'll end up with more information on that. Our weekly social is on Wednesday nights at 7 p.m. with the Zoom link being sent to the Kingston Center email list, and Susan is our hostess for that. And we are on YouTube, so look under the RASC-Kingston channel. This meeting will be scheduled there once it runs through its compression, and it should be up in a day or two. We're at Twitter at Astro-Kingston, and we're on Facebook under the RASC-Kingston Center group. So if we are finished our regular meeting, oh, no, one more poll apparently.
No, polling definitely doesn't work for me.
Yeah, I think you gotta have boxes.
Unfortunately, I can't see your end of it. I'll have to experiment with this some more to see what the end user sees. But we've got 14 responses so far, and we'll give it another 5 seconds here or so. 3, 2, 1. Okay, let's end the poll and share the results. Oh, super duper impressed is the winner. Oh, or is it tied with I'm very impressed? Oh my goodness.
Excellent. Okay, so I guess that finishes our official regular meeting, so we can shut the YouTube presence live stream off. And if there's anybody that has any questions or just wants to chit chat, now you can